Yeah, this now was a break for video number 29. So that now the next part is viewed in video 30. Some words to the bode plot of PIDT1 in chapter 5 of this lecture. We use the bode plot as a base information to design controllers. So we also have to work with a bode plot of PIDT1 because, of course, this is a standard classical controller we will use in many applications. So what we can check is how can we convert the transfer function into the bode plot equations. Very simple, by converting the transfer function into the complex frequency response. We replace all p's into j omegas and write the expression then in this form. Or I want to express this for step. No, let's go with this. And for this we now can write the expression for the magnitude of a PIDT1 block. We have a division line, and we of course use now the knowledge, the equation, the relation that the magnitude of this type is the product of the magnitude of the single parts. So we just convert each single part, this PD part, this PD part, this PT1 part, and this integrator into the magnitude values, and then can multiply these magnitude values. It gives the following expression. Kc, of course, is the main constant in front. Omega Tn, j omega Tn is pure imaginary. The magnitude of an imaginary number is the imaginary part itself. But this 1 plus j omega Tn is real part plus j omega Tn, this is the imaginary part. We have to use 3 times the Pythagoras equation. 1 plus imaginary part squared is omega Tn squared multiplied with square root function 1 plus omega Tv squared, and its denominator finally 1 plus omega T1 squared. With the phase we can do the same. The phase of a PIDT1 is the sum of the phases of this single factors in my expression. So let's start with this. A pure imaginary part in the denominator always gives a minus 90-degree value, and in 1 plus j omega Tn part in the numerator is a positive arctangent of imaginary divided by real part, so arctangent omega Tn plus next arctangent omega Tv minus the arctangent of the PT1 minus arctangent omega T1. So this is the phase equation for the bode plot, and this is the magnitude equation for the bode plot. We have drawn the bode plot of the PI. We have drawn the bode plot of the PDT1, and the PIDT1 bode plot is nothing else than the sum of both diagrams. So first, magnitude curve. F magnitude, don't forget the conversion into the dB value, logarithmic axis, and I show you now a very quick manual construction of the asymptotical curves of a PIDT1. First, you have to mark the 3 corner frequencies. And now note in control systems. So in this lecture, we always have Tn is larger Tv, because we select Tn and Tv value with the pole compensation, and Tn is selected to the largest process time constant, Tv to the second largest process time constant. So our selection forced this is true, and step depths larger 1, because this gives an acceleration. That means Tv is larger than T1. So we mark in our omega axis the omega n value here, the omega v value here, and the omega 1 value here, with the following expressions. Omega n is the inverse of the Tn, omega v is the inverse of the Tv, and omega 1 is just the inverse of the T1 value. And with these relations, we get this order. On the left part we get omega n, then in the middle we have omega v, and in the left part, on the right part, we have omega 1. Now, this curve can be constructed in the following very simple way, asymptotically. First, we draw a horizontal line from omega n to omega v. Start. This is a 0 dB line. The distance to the 0 dB line is nothing else than Kc in dB. So Kc should be known, convert into dB value, and then this gives a distance to the 0 dB value. So if Kc is larger than 1, we are over the 0 dB line. If Kc is smaller than 1, we are at the bottom of the 0 dB line. Then next point is, starting from this point, draw a gradient, a straight line curve with a negative 20 dB over a decade. That is the integrating part coming from this integrator. And starting with this cross point, draw the curve with positive 20 dB over decade gradient that comes from the PD part. So we see here, this is the PI bode plot magnitude curve, and now this is the PD part, and finally this comes at T1. So at omega 1 we go up and see at this cross point, this cross point, then make the next curve as a horizontal curve crossing the D part at frequency omega 1. If you have done this, control, check, this should be step depths in dB. Now that is again a high frequency gain increase defined by the step depths. Don't forget, the step depths is the ratio of Tv divided by T1. Step depths in dB is exactly the distance between the middle frequency gain to the high frequency gain. Did you find this step? So if you have all these points and know what plus 20 dB over decade and negative 20 dB over decade is, then the construction is done in a few minutes. You only need the 3 radian frequencies without 2 pi here. No 2 pi. If you have an f axis, of course, then you have to divide all values here by 2 pi. and the correct curve, of course, then has a 3 dB point here, a 3 dB point here, 3 dB over the corner frequency, 3 dB over the corner frequency, and here a 3 dB point under the corner frequency. And then you can be sure that in the middle we have a cross point of the asymptotical curves. So we can very quickly draw these points. For low frequencies we have this curve. You see with a little cool hand I can draw the curve very accurately if I have a previous asymptotical construction. So this is one way to draw the bode plot of a PIDT1. In the lab you should measure the bode plot of a PIDT1, and of course you should prepare the bode plot. You should draw the bode plot in millimeter paper in this way, and then you can compare the measurement with your preparation at home. The phase curve. Yeah, the phase curve is shown in the workbook, page 16. I go to the workbook, go to page 16. Yeah, that's not too far. Oh, das gibt's doch gar nicht. Page 16, in the PIDT1 row, we have here row 14. You see, this is a construction we have done yet. This is a step response. This is a transfer function. Here you see the summing form and the bode form. And here you see the phase curve. Note that we start for very low frequencies with -90. Then the PI pulses up, the PD pulses over the positive range, and then the PT1 pulls it down to 0 degrees. So we have here a positive region and a negative region. Sometimes this knowledge helps in understanding the function in a closed loop system. But note, this bode plot gives no information how a PIDT1 works in a closed loop system. This comes later in our next project. You will see some properties of a PIDT1. Okay. Last word, very important information. Sometimes this is useful to know. The DC gain of the PID controller is how large. Some people like to read this DC gain value here. Please don't do this. This is not omega 0. Omega 0 is not in this diagram available. Omega 0 is infinitely large on the left side. Yeah? Logarithmic scaling means logarithmic 0 is negative infinity. So the DC value is not in this plan. What you can see here is if you have a ramp here with -20 dB over decade, so this is an increase which is never ending. So we can say the DC gain of a PIDT1 is infinity. Don't forget it. You can see this, of course, here in this magnitude curve. If you replace omega with 0, you see this is 1, this is 1, this is 1, this is Kc. But here if we divide by omega 0, and then the magnitude goes to infinity. So f magnitude of omega is 0 goes to infinity. That is the DC gain. We have a large, very large DC gain. And the high frequency gain is this. If this is Kc and this is step depth, if we add both values, so we can say the high frequency gain, f omega, is very large. Magnitude is Kc times step depth, the value of the peak at time 0. Yeah, so the in the frequency domain, the high frequency values defines in the time domain the small time values. That is Laplace transformation. I think that's all for PIDT1.